That's it. Okay. Today I'm going to talk about total positivity. And if time permits, I will talk about double Brière cells. But let me start slowly. First, I want to recall a point where we stopped last time. Last time we discussed Laurent phenomenon. Let me recall what is it. So assume that we have certain seed. I want to recall that seed is a pair of combinatorial data, like quiver or antisymmetric matrix, and also set of variables, a1, an, and probably some of them are frozen. Maybe my favorite notation will be to put here m. We define the so-called mutation, which is transformation from one seed to another, and draw this through the graph, not oriented graph, where two vertices are connected by arrow if there is a mutation from one to another. This edges are actually labeled. We can mutate in any vertex, and so these edges are labeled by the vertex in which we mutate. And the theorem, due to Fomin-Zelevinsky, which we proved last time, states the following: that if you take any sequence of mutations, say d mutations, then variables that we obtain after the sequence of mutations are Laurent polynomials, actually with integer coefficients, from the variables which we have on the initial seed. This is Laurent phenomenon. Okay. I want to spend some time to prove a slight enhancement of this theorem, name which I already stated here, which says the following: these variables are Laurent polynomials, but they are Laurent only on unfrozen variables. So they belong to this following ring: polynomials which are Laurent on first n variables, and not Laurent, just ordinary polynomials in last n minus m variables. In other words, the frozen variables cannot appear in denominator. If you remember, so the rule of mutation was as follows: so if you mutate in some variables ak, the rule was as follows: so a new variable ak prime is equal to rational function. In the denominator we have ak, and in the numerator we have some product over bak greater than 0 ai in power bak plus product over bak less than 0 ai in power minus bak. So some stuff like this. And it is clear from this formula that unfrozen variables can appear in the denominator just from the first mutation. But in frozen variable we cannot mutate, so at least from the first, after the first mutation, they do not appear in the denominator. But of course, they appear here in some numerator, and then we will divide. So who knows? Maybe we'll have them in the denominator. And so the theorem says that this is not going to happen. Okay. Are there any questions now? I prefer to start slowly. Maybe somebody else can come, and if there are some questions, maybe I should recall something. Okay.
Sorry. By edges we denote mutations, right? Or I miss?
Yes.
Okay.
Okay. Now the proof. proof will proceed by induction. On D, number of mutations. And using this induction, we will first prove the following lemma. That it's called. So if we take some AI on after some quantity and consider it as a function on frozen variable. I don't know, R. So this function is a rational function. Rational non-zero function. No, rational. Sorry. Set such that if we set AR equal to 0, we get subtraction-free expression. Let me think once again how to state it. Just a moment. So let me say it once again. So we consider any function as a rational function on the frozen variable AR. So we fix some AR. Then we know that this is a Laurent polynomial. Okay, let me don't put this as a lemma, just as an idea, as a statement. So we consider as a function on frozen variable AR. We know from the Laurent phenomenon this is a Laurent polynomial, and we want to prove that that this is not Laurent. This is actually that we want to prove that this is not Laurent polynomial, but this is standard polynomial. We have only positive powers of AR. What we will choose the function of AR. So we will claim that AI of TD, if we substitute AR equal to 0, is a subtraction-free how to say it better. Sorry, I thought that this proof will be the main problem of today's lecture, so maybe I should work out it more in the preparation. Anyway, so what we want to prove. Want to prove that this if you substitute AR equal to 0, that this is not equal to 0 and not equal to infinity. We want to prove that this is not equal to infinity. This is equivalent to the fact that that on the previous step, the corresponding variable is not equal to 0. So we proceed by induction, and we want to prove by induction that that we don't have AR in denominator. So if you substitute AR equals 0, we don't have pole. It is equivalent to prove that actually we don't have the 0, because the only way to get pole is that if we divide by 0. Okay. Now how to observe this? So assume that we make some mutation and get new AK prime. It is equal to sum of two monomials divided over AK. And now we want to substitute R equal to 0. Note the following. Note that first, let me note that AR appears in no more than one. It appears in either appears in one of the monomials, or cannot appear in both in M1 and M2. Is it clear?
We should look at the formula for mutation or what?
Yes, you should remember
okay.
the definition of M1 and M2, yes. But I mean, this was not answer. Is it so? Should I recall something or? So M1 is a product for BAK greater than 0, AI in power some. I mean, some AI in some step. This TD minus 1 actually, but it doesn't matter in power BAK. And M2 in the opposite product. So one of them is a product from which from variables which correspond to vertices where h going to k, and another from the vertices from which h is going from k. So AR cannot appear, is either connected to k by edges. So BKR either positive or negative or 0. So if BKR is 0, then R doesn't appear at all. Other one, it appears only on 1, 2. Okay, and second, if any A R AK AJ on the previous step. If we substitute AR minus 1, AR equal to 0, can we has a form of subtraction, has form of subtraction free rational function. So some form like, I don't know, I have P over Q, where P, Q are rational functions where there's no substitution, only summation. So we prove, so this is, I mean, one more statement which we have to prove by induction. In the base, where in the initial step, this is obvious. And then if we perform some mutation, we get some term like, we get expression like this. And you see, here we have only summations. And if we add term subtraction-free expressions, we get again subtraction-free expression. If we divide subtraction-free expression, we again get subtraction-free expression. So in the definition of mutation, we don't have substitution. So any variable, anything is subtraction-free. And if we put AR equals 0, it means that we can just omit some terms, but if we had subtraction-free expression, we still have, it remains subtraction-free. And why I'm very interested to this, because if M1 and M2 are both non-zero, then in numerator we have sum of two subtraction-free expressions for AR equals 0, which cannot be 0. So if AR appears in one of these terms, then for AR equals 0, this corresponding term vanishes, and we get some term which is not vanished, which don't have AR, so and no other term vanish when AR equals 0, so we have something non-zero in numerator, something non-zero in denominator, so we have some non-zero and not-infinity expression. And if AR appears in both terms, then in the numerator we get a sum for AR equals 0, we get sum of two subtraction-free expressions, which is again subtraction-free, so non-zero. So actually, so maybe I should organize it another way. So actually, we argue by induction, and by induction we prove that any cluster variable for AR equals 0 is non-zero subtraction-free rational function. And that's it. Are there any questions?
Can you recall? Maybe I didn't understand. What do you mean by subtraction-free?
It is a rational function where so ratio of two polynomials, in each of them we don't have substitution, only summation. Polynomials with integer coefficients, integer positive coefficients.
Substitution. It is
don't have subtraction. We don't have subtraction.
Subtraction. Oh, sorry. Okay, I understand.
Example. I don't know. So the standard interesting example is the following: that we can take the following polynomial x squared minus xy plus y squared, and this is actually subtraction-free rational function because this is x cubed plus y cubed over x plus y. So to be a subtraction-free expression, it is not absolutely obvious condition. So in particular, no, I mean, it means it does means that you cannot write any formula with minuses. But in particular, it means that for positive values of variables, the value of the correspondential function is positive. Okay. Are there any more questions? Okay, no questions. Let me. So the theorem is proved. In particular, the theorem means that in recursion relations, I don't know, like Thomas relation, it can be shown that it depends on the coefficients in this relation do not appear as the denominator. So for any integrality holds if we just assume that original values are ones. Okay, maybe this is difficult to say clear. Let me ignore. Let's ignore this comment. Okay, what I want to say is that this is subtraction free rational function. Okay, now I want to give a remark. So actually at this point we know two things. First, we know that any variable after demutations is Laurent polynomial on variables in the original seed. As I just said, it is just polynomial on the frozen variables, but it is not important. On the other hand, it is quite obvious that this is subtraction free rational function. Sorry. Wait. No, here. I see. Is subtraction-free rational functions on original cluster variables. So we mutate step by step, and in each step, we have subtraction-free rational function. We sum them, divide them. It's natural to guess, looking to these two statements, there is a statement which unifies them. Namely, that there is a theorem, but I mean, so both this statement is due to Fomin-Zelinsky, and this is, I mean, obvious observation, which is again, I mean, it's just a definition. So it's known when the cluster algebras appears. But the theorem which I'm now going to state is hard and much more recent. And theorem said that FTD are actually Laurent polynomials on the same variables with coefficients with positive coefficients. Here coefficients are just integers. The previous example shows that Laurent polynomial, which is abstraction-free rational function, is not necessary to have positive coefficients. So this is not just a consequence of these two statements which we have, but this is true. And as I know, there is no elementary. Okay, maybe. Okay, I don't know. Actually, I don't know what. So now at least I think yes, there is no elementary proof of this fact. The proof involves some categorification stuff, but I'm not going to discuss it today and probably in the course at all. Other questions?
Sorry, but I don't understand how just how minus can appear if we take mutations. Maybe I just don't remember formula precisely. We have sum of two like monomials, right?
Yes.
Where
and one,
both monomials are like subtraction-free rational function.
Yes.
So I thought minus just cannot appear.
Yes, this is how you explain that this will subtraction-free rational functions, not Laurent polynomial, rational function.
Okay.
Why it will be subtraction-free Laurent polynomial? Why, if you divide numerator of the denominator, you will not have minus?
I thought all our denominators in this like subtraction-free rational functions will be monomials. So
why? In first mutation, yes, but on the 10th mutation, why? They will be our variables. Variable is polynomial.
Okay, well, I see on the example.
So this is a strength of the, Laurent phenomenon is a very non-trivial statement. That you actually have non-trivial polynomial on numerator and denominator, but occasionally one is a factor of another. Okay. Okay. As I tried to say you a couple of times, so in the origin of the cluster algebras, there are two phenomena. One of them is Laurent, and another is important property, or I don't know, is the positivity. Another important property is positivity. And positivity, it is hidden. It usually follows from the fact that expressions which we get are subtraction-free. So if, for example, variables for initial cluster are all positive, then variables which we get for new cluster are also positive. You see. Let me discuss an example which may be interesting in itself, which was quite studied even before origins of the cluster algebra, but in other sense was one of the motivation of the cluster algebras. Okay, so I will go on to discuss matrices. I will have matrix. Okay, M will be n times n matrix. So now the new topic. I mean, you can, if you missed something before, you now can listen just once again. So M is n by n matrix. I can denote its submatrix by M I1 AK G1 GK submatrix. Indices subscripts are stands for rows, numbers, and superscripts stands for columns. And we will quite often use their minors. So if we have D ij is a D of some set of rows, E1 AK, G1 GK is a determinant of M I1 AK G1 GK. Here I usually will assume that E1 is in G1 are ordered. I's and G's are ordered. Okay, definition. Matrix M is called totally positive if delta if delta ij greater than 0 for any subsets I and j of the same cardinality. This definition was introduced maybe now more than 100 years ago, and there are it was motivated not by cluster algebras or combinatorics, by some applications to mechanics, to I don't know, many things. So just to give you some spirit of the of what is it about, let me first state the well-known theorem, which is not about totally positive matrices, but just about just positive matrices. So there's a theorem due to okay, maybe if Perron-Frobenius, maybe order should be opposite. I don't know why it is like this. Yes, theorem by Perron-Frobenius, which states the following. So if M is positive, so if M is such that any matrix elements of Mij greater than 0, and let lambda be a maximal eigenvalue by the absolute value of lambda. The eigenvalue with maximal then the following are true. First, lambda is actually real and positive. Second, lambda has no degeneracy. And the corresponding if some v is eigenvector, then all vi have the same sign.
This is eigenvector which corresponds to this lambda or
Yes.
any eigenvector?
Yeah, no. Correspond to this lambda. I mean, I suppose many of you heard about this theorem. If not, just look to the Wikipedia and you find a lot of applications on this well known. It has very well-known meaning as a theory of probability and so Markov chain and so on. And there is a just very nice and natural analog of this for the totally positive matrices. So theorem, and this theorem is due to Gantmacher and Cree. It was published in their book in the end of the 30s. But maybe. So if matrix M is totally positive, then the following are true. First, its eigenvalues are all positive and distinct.
And they're all real?
You see, greater than 0. Yes, all real. And there is a similar statement similar to this one. Let me copy and just correct. So if we have eigenvector which corresponds to, say, G's V, then it's no longer true that all Vi have the same sign. Then in the then in this sequence V1 Vn. If you want, I can add here additional index. then the sequence of v1j, vnj has exactly g minus 1 changes of sign. So for g equal 1, all of them has the same sign. For g equal 2, we have first some set of, say, pluses and then some set of minuses, and so this is, I mean, this elementary, how to say, this theorem is a good exercise in linear algebra if you want, like Perron's theorem. So I even put it as a problem. Okay, let me label this not by items, by A and B. Prove A above. It is quite nice consequence of the Perron-Frobenius theorem. Okay, this all is just motivation why these matrices are interesting. You can ask whether such matrices exist or how many such matrices. Let me give you an example. Okay, first let's consider 2 by 2 case. Then how to write down this matrix. One can write, say, A, B, C. Here one can write D, but then you will have some sort of non-trivial conditions that determinant is, some condition determinant is positive, but you can just write here, use another way. You can write here again B, here A, B, here B, C, so divide, and here you can write A, B, C plus D. And this is a parameterization of totally positive matrix in terms of positive numbers. So if all these numbers A, B, C, and D are positive, then we get totally positive matrix, and vice versa. And actually, exists similar parameterization exists for 3 times 3 case. Okay, maybe I will not write it for speed, but I want to pose, I mean, 2 natural, I mean, at least algebraical questions. First is to, I don't know, somehow classify or parameterize totally positive matrices. And another question is efficient test for total positivity. What do I mean here? By the definition, total positivity means that all minors are positive. And by definition, all minors, there are quite a lot of minors, like 2n minus 1, 2n choose n minus 1, because you have to first specify k and then pick k columns which you use, and better to pick n minus k rows which you don't use. So in total, you should pick n numbers from 2n. So this is 2n minus n and minus 1 because empty doesn't give you a check. And okay, anyway, this number is quite big, like some exponent. And for n, for great n, it is not efficient to check. But it appears that it is not necessary to check so many, and efficiency test is quite small. And this is what I'm going to talk now, and maybe I will return to parameterization next time. And cluster algebras somehow gives you answer to these problems. Okay, any questions? Okay, let me switch on the light in my room and then. The answer which I'm going to propose today will be quite combinatorial. So now I'm going to give you some set of combinatorial definitions, which from the first, I mean, at least in 2 or 3 pages, at least 2, will look completely unrelated to what we discussed before. And it can be made more motivated, but I will not. I'm not succeed to this, so now we'll see some not very well motivated combinatorial definitions.
So, sorry.
Yes.
Why is there -1? I didn't understand in the last computation.
No, for n equal 2, how many minors you should check?
4 and then one more, so 5. All right.
5. Okay, and what you get by 2 and choose n minus 1?
Probably 6. Okay.
2 and choose n is 6 and minus 1 is 5. So.
Yes, yes.
And difference is empty minor. There are no rows, no columns.
Ah, okay.
Okay. Okay, we'll have some networks. Something. Which I didn't erase. So network will consist of n parallel lines. I will draw these lines in such teal color. Between these lines, we will have segments which connect these lines, and the segments could go, the lines somehow directed, could be viewed as directed from left to right, and this. Okay, the segments looks either like this or like this. So on this set of lines, I will draw a graph, which will be first of all two-colored. So vertices will be either white or black. I will call it black, despite the fact that I pick another color, teal color. And all segments between lines should be colored like this. So white is on the left and black comes on the right. And segments are not perpendicular to this line, they are like this. And if after such addition of the segments, you will have some graph. It could be not, it is not very essential, but very important, but I prefer to make it bipartite. For this reason, if the graph will be not bipartite, for example, we have 2 black vertices which are connected by H, then you just insert additional vertex to make this graph bipartite. This is a network which will be in form of bipartite graph. So it will be. I hope this bipartite graph will appear in the course several times. There are many combinatorial things, avatars or combinatorial tools in this science, and I like bipartite graph, so I will try to use this more. Okay, here are a couple of examples of the network. So we have 3 lines. It is not very important, but you can think that network is oriented from left to right. But maybe for what I'm going to say now, it is not very essential. So I just delete all these arrows. So this orientation will be important next time when I will write some parameterization, some. Okay, I hope I deleted all arrows, which is not important for now. And the net combinatorial tool will be zigzag path. So I will now draw some passes on this graph, which are zigzag. What does it mean? It means that this path goes right on any black vertex and goes left on any white vertex. Here is a symbolic example of such path, and now I will plan to draw them on precisely these networks. For example, let me start from the vertex 1. I start. Is it visible?
Yes.
Okay. Yes. I start. Then you see black vertex. In the black, I go right, so nothing. White vertex. I go left, but this is a vertex of degree 2, so again nothing. Black, go right, again nothing. Now white, and here we first have chance to do something. So what do we? I mean, in my notes I have some way to write down this graph, so I try to follow it. So in here we'll move left. Here again black we move right. Here white we move left. Here black we move right. Okay, and this is the result.
Can I ask?
Yes.
We can have only valency-free vertices, and or two, free or two, right? Or,
yes.
okay.
In figure, in networks which we study, we only have such values. Okay, now we can go from this near the second line. So assume here we go. On the white we move left. So in this case means that we don't do nothing. Black we move right, nothing. White move left, nothing. Here black, we should move right. It means that we actually intersect the zigzag appears here. So theoretically, by my definition, this zigzag is a path which goes on the graph. But if I'll draw on the graph, it will be difficult to understand the situation where we go on the same edge in two directions. Any edge belongs to two two zigzags. Maybe I should write it. So here I draw them a zigzag not on the graph, but somehow near the graph, so that we can actually somehow perturb a bit my graph, my path, my zigzag path, in order to visualize it. Anyway, so I now studying this zigzag. It moved right on this black vertex. Next black vertex of the valency 2, so nothing to do. And now we have white vertex. Here we again should maybe how to do it this way and then this way. Okay, and similar we can study zigzag which starts from 3. It goes here on the white move left, means nothing. Here it's clear that we should do something, and the black move right, so it means that we intersection appears here. Sorry, something like this. Then some time, and on the black move right. So here. Okay. If you're still following, did we draw all zigzag paths or something remains? How do you...
Probably if we take like starting point, then it's fixed.
Yes.
So it's so.
Any other suggestions? So all zigzags which we now wrote, they go from left to right. So they're all, we have draw n zigzags, which goes from left to right. But there are zigzags which goes from right to left. So we can see with this 1, 2, 3 could be not starting points, but end points of the zigzag. So for example, one can start here. Here. Then move left on the white, move left. So nothing. On valency 2, nothing. On the white, move left, nothing. Now on the black, move right. And that we should, here we should do something like this. On the black, move right. Something like this. And exit. So these are zigzags which goes in the opposite direction. Should draw by green. Again, we have n such zigzags. For completeness, let me draw all other. So this one goes like this. Then here like this. Here like this. And here it returns. And the last one starts here. The 6. Like this. Now this is all, because we cannot. So it is easy to see what can happen for zigzags. If we have a situation like this, then green zigzags do not see it; they are parallel, and orange zigzags they have intersection. And for a situation like this, the situation is opposite. So in some sense, you can think that we have two like braid. This is sometimes called the diagram. I prefer bipartite graph conventions, but if you quite often people prefer just to draw zigzag passes, and this is called double wiring diagrams. So we have two sets, two networks. One is which is drawn by orange, another by green, and they intersect like braids intersect for the braid group. Now, in principle, one can study any diagram like this, but we will assume the following properties. That any two zigzags of the same color intersect exactly once. You can see this in my example. So, for example, this and this intersect here. Similar. There is another way. So in other terms, equivalently, not equivalently, from the, it follows from this that zigzags of any color give permutation of the form W0 1 2 n minus 1 the longest permutation. Again, here we have 1 2 3, but after the end 1 is the largest, 2 in the middle, 3 in the bottom. And here similar for green. And this follows from the fact that any two zigzags intersect only once. So for any two, I don't know, if their starting points are I and J, then the corresponding zigzag intersects once, so their order will be changed, will be opposite. And so this is a corollary. If you want to state this not as a corollary but as equivalence, it means that we have actually we have two reduced expressions of reduced decompositions of W0 in terms of generators of two permutation groups. So we either permute orange zigzags or green zigzags. Permutation of orange I denote by SI bar, of green of SI. So if we look for the edges or intermediate edges of this type, we get some product of the reflections which correspond to which of bar reflections, and this should be this product should give you W0, and this condition that exactly once means that this will be reduced decomposition. For example, it will consist of exactly n choose 2 products, and similarly for SIs. So the fact that it will be exactly 1 just means that it will be shortest possible decomposition. Okay.
What is SI? It is some map or what?
SI is a simple reflection in the permutation group.
Yes, but it acts on network.
If you want it acts on zigzags. We can label zigzag by their starting points. So green labeled by 1, 2, 3, and orange labeled by 1, 2, 3. And SI permute green zigzags, and SI bar permute orange zigzags, as you see here.
But how this related to intersections? If we permute them, we don't change like situation.
You permute. So here you have zigzag. Here zigzag number I was below zigzag number I plus 1, and after this SI, after this intersection, the order will be opposite. This is what permutation do.
Okay, sorry, I didn't understand. Zigzag is fixed by its starting point and network.
Zigzags are labeled by their starting points. If you have network, then to network you can assign a word in the language SI bar, because for any such edge you can assign either SI bar or SI. And if you look to the SIs, this word, you will have reduced decomposition of the W0. And if you look at SI bar, you also have reduced decomposition of W0.
Okay, we can, you mean that we can like decompose network to some kind of product of SIs, or?
Yes.
Okay.
Okay, and now let me, so this is not all, but now combinatorial stuff which we need, but now we can more or less return to the our original problem, and now we can how all this related to totally positive matrices. So definition: to any phase we assign the minor, and a number of rows to phase for graph. It's clear. It's just subset. It is a connected component to the complement, and number of rows it will be orange zigzags below the corresponding face, and number of columns will be numbers of green zigzags below the corresponding face. Here are a couple of examples. I don't know whether it's, of course, it's hard to follow just from the first glance. So what can we see from these examples? So first of all, what happens near the border? Near the border, here the orange zigzags only starts. So here we have 1, here we have 1, 2, here we have 1, 2, 3. Generally. And near another border, green zigzags starts. So we have again 1, 1, 2, 1, 2, 3. And for green zigzag comes here after the complete permutation. So on the bottom we have n. Here we have n minus 1, n. Here we have n minus 2, n minus 1, n. And so on. And similar on the right bottom. So here we get n, here we get n minus 1, n. Here we get n minus 2, n minus 1. So in any case, we get the following. So these are the minors which are like this. So the anti-diagonal principal minors. And these principal minors, they appear in any network. Okay, so the border does not depend on the network. It depends under our conditions that both orange and green zigzags perform total permutation, perform longest permutation. About internal pulse, this is not longer true. So, for example, see here you have a lot of faces near the bottom. So you have a lot of minors which are just matrix elements: 1, 2, 1, 1, 2, 1. And here you have only one such minor, but you have many minors which are 2 times 2, 2 by 2. So internal part depends on the type of the permutation. Maybe I can also comment the following, that on the here on the first figure, all minors which you have, they are initial minors. And I draw by picture what is its initial minor. It is a minor which is constructed as follows. You take some element, go by diagonal till you meet the border, and take the corresponding minor. So this is the minors which you can, which are first of all solid. So the set of rows makes segment, the set of columns makes segment, and they cannot be moved in this direction. This is a set of minors which appear here. So this more precise, this 3 by 3. So first you have this 3 just matrix element, then you get this such 3 2 by 2 matrices and 3 by 3. It's just always. And here this it is become another set of minors. Okay. Now let us discuss one more thing. Okay, let us discuss one more thing. How many minors do we have? How to compute? For example, how many minors do we get here? Who can compute?
Nine.
9. And here? I hope again 9. So you can now guess the total number of minors is equal to what you can guess. You can guess, I think, n squared. And why it is so? Because at the beginning you have n faces. At the beginning, I mean before any age, and then after each age you close one face and opens another face. So each age increase number of faces by 1, and number of ages will be n choose 2 for orange zigzags and choose 2 for green zigzags. So this is n plus n choose 2 plus n choose 2. So number of minors is fixed. It isn't squared. And from for this minus sum, 2n minus 1 minors, which correspond to not closed faces. So they're on the boundary, and all others, like n squared minus 10 plus n minus 1 squared minus, belongs to the internal part. Okay, this is how I connect this story about bipartite graph and networks to the totally positive matrices. And now I will connect them to the story about cluster algebras. But in order to do this, I have to draw a quiver. Maybe for speed up, I copy the picture from some Russian notes. And so this new point, it's a big point, which says the quiver. And first of all, this is how it looks like. So I use different colors. So this is teal color, which is original bipartite graph, and the quiver is this green-like color. I will think how, I don't know, maybe somebody knows how to call this color. And the rule is the following: so that around, maybe this is not the best picture. Anyway, and the rule is the following: that around black vertices. Sorry. So the quiver is constructed like this. So for vertices of the quiver, they correspond to faces of graph. And edges are oriented like this, around black vertex. Edges goes clockwise, and around white vertex contour clockwise. Like here. So this is a counterclockwise around white vertex and clockwise around black vertex. Now, I mean, I think it remains near the 5 minutes. I have to state, maybe we'll not have switch time to explain them, so I leave everything the problems, but at least to state the main theorems. So theorem, first theorem says the following, that any two networks, maybe this picture is not necessary, at any two are connected by transformation, by sequence of the following transformations. Transformations, again, for speed up, I copy the figures from another file. This is transformation 1. This is transformation 2. And this is transformation 3. This is a combinatorial statement. I will comment it in a minute, but let me first finish the main line of arguments and then return to the question. Second theorem. These transformations are mutations. So what do I mean? That at this point, I constructed quiver, and I have variables which I assigned to each phase. So actually, at this point, I have seed. To any network, we assign seed, which consists of this quiver Q, which you construct here, and deltas ij, which we defined here. Now, what this theorem says, that for any transformation which we do here, if ABC, if I put here corresponding minors, they actually satisfy quadratic relations which are necessary for the mutation. And last theorem, but I think I will all the theorems are more or less straightforward. I put them maybe as hint to the problem. Last theorem that says that any delta ij, any minor, appears in some network. And corollary from all this story if for given network all delta j greater than 0, then all delta j which are greater than 0. So it is as a corollary we get an efficient criterion how to check that matrix is totally positive. You have to check only minors which appears in some network. So you can pick your favorite network, for example, this one. And you can check only these initial minors. And if they are positive, then all minors are totally positive. Okay. Now, so I mean, I come to the final point of to which I wanted to come, and now maybe questions, because I clearly speed up.
I want to ask a question. So, what does Si plus 1 Si equals Si plus 1, this spread relation, what does this mean?
Thank you for the question. This is actually what I wanted to comment. So I will say about this also next time, but what is the meaning of this theorem about transformation? We have some, to each edge we assign either Si or Si bar. And we have some, therefore we have a certain word in terms of this S's. And actually this theorem means that it's, I forgot whose theorem, that any reduced, the transformation from one reduced word to another word can be performed using only the braid relations. So these are, so here you see for such edges I assign S, but here we have two edges, two Si plus ones and one Si, and here you have two SIs, one Si plus one. So relation between these two networks in terms of the permutation means exactly this.
Okay, thank you.
Maybe I can also comment that first means is the same but for bars. So Si bar, Si plus 1 bar, Si bar is equal to Si plus 1 bar, Si bar, Si plus 1 bar. And the last, it is a relation for, which means that we have a product of two while groups. So in some sense, non-reduced, not simple root system. Anyway, so it is this relation. So these two while groups commute. In principle, you can ask where commutativity between Si and Sj, where I minus j is greater than 1, but this commutativity will be trivial if you permute Si and Sj which are far away from each other. The set of minors will not change. But for such transformation, set of minor changes and exactly according to the mutation. In this case, you have this relation xy is equal to AC plus bt. And this is the implementation. More questions?
So by this equality, you mean that they are like mutationally equivalent or something more?
So this equality is some statement about minors.
No, right equality.
This statement, so this is a statement about you have matrix and you have some relation between its minors. So for example, in this case, if you let me write this. And let us assume for simplicity that this is just 2 by 2 case. So here 1 and 2. Then by definition, then B is equal to 1. Then okay, let me how to do this. Let me copy it again. Now write down marks for all these minors. So this is just 1. This is a determinant M12 delta 1, 2, delta 1, 2. And on the left, we have, what's my convention? Delta 1, 2, here, delta 1, 2, again, delta. And on the middle, I need to recheck, but in one case, we should have delta 1, 1, and in another case, delta 2, 2. So the meaning of this relation which I wrote was the following, that delta 1, 1 times delta 2, 2 is equal to delta 1, 2, 1, 2 plus delta 1, 2, delta 2, 1. So this is the formula for the determinant. If you substitute this to the left side, it will be a standard formula for the determinant 2 by 2 matrix.
Yes, okay, I understand, but I was talking about equality like as braid relation. By braid relation, we mean just the same. Yes.
So we have braid relation. How to say? So the braid relation is a certain transformation of the network. The braid relation says that there exists such transformation of the network which will still which preserve our conditions, that any two zigzags intersect only once. And then you can ask, okay, so what happens with cluster variables? And it appears that minors, which I put you just without any explanation, just put you, which from some book, it appears that these minors exactly satisfy a mutation relation.
Okay, thank you. May I ask one more question? Or
yes.
I don't know. Okay, well, it's above a bit. When we correspond minors to faces, we say what? We say that number of minors is marked by two zigzags which goes below face, right?
And for each face we assign minor, and number of rows correspond to zigzag, orange zigzags below this face, and columns to green zigzags below.
But we have, like, for the case pictured, where to say 1, 2, 1, 2, we have 3 edges below face, right?
This picture.
Yes, on this picture.
This 1, 2, 1, 2.
No, 1, 2, 1, 2.
This, okay.
This.
Yes, we have 2 edges below the face. Yes.
I thought 3 because At first I thought about edge.
Let us look here. So you're talking about this face.
Yes.
And you have two orange zigzags which goes below it, and two green zigzags.
And
zigzag cannot intersect face because it goes actually on edges. So neither below or upper.
So okay, but it's for so we can have like more than.
I mean, the number of zigzags is, so if you look to the face, then you can count the horizontal edges below it, number of lines below it, and this will be the size of the corresponding line.
So it can be like more than one like orange zigzag.
I mean, for faces on between the first and second line, it will be always one orange and one green. Between second and third line, it will be always two orange, two green, and so on.
Okay.
No, maybe I'm not explaining, but I'm fixing what is clear from this example. So here you have -1 by 1. Here you have -2 by 2. And here -1, 3 by 3. Maybe it is easy to believe it.
Sorry. Okay, it's 1, 2. Here it's 1 and 2. It's two zigzags, right? Or two orange
this
zigzags.
or
No.
here?
This here.
Two orange zigzags below this. Yes.
It's zigzag number 1 and zigzag number 2. No, we don't have orange zigzags with number 1, 2. I thought we have, because like in
no, this is two zigzag number 1. I mean, I could put comma here, but it will be too much commas.
Okay. I thought we have, because in the picture below it seems like that. Sorry.
What?
Okay.
Sorry. We
No.
have 3 zigzags.
More,
1,
more.
2, and 3.
Below.
Below where?
Where? Here.
Here. What?
Okay, sorry.
1, 2 zigzags.
Yes, I thought it is number of zigzag which starts here. Okay, now I understand.
Okay. I should stop, at least formally.